Hello everyone. Today we're going to look into how to pick solvers for your models, specifically assuming you've got Simscape and Simscape Electrical specifically in them. We're not getting into what's going on behind the scenes, we're getting into how to pick a solver. We can dig more into the technical nuances of them later, but you don't actually need to understand that to know the basic rules of thumb for how to experiment and see which solvers are going to work best for you. So I've got a DAB converter here. A DAB converter, if you're not familiar with it, it's an isolated converter, DC to DC, and it works by controlling the phase of this set of half bridges to here. So you'll have a square wave on one side, and you'll have another square wave that is same duty cycle typically, but offset. And this lets you control the direction of current through the inductor and transformer. This is really useful for this particular application of looking at solvers because that's actually a harder problem for solvers to deal with. You have to accurately capture the width of the duty cycle, and you have to actually capture the phase offset between the two cycles. So there's a lot of tricks that certain software might use under the hood that won't work in this case. So this is a harder one to see in optimization, if any, and so it's good to show how those optimizations might break down the accuracy of a solver, and that will show up very clearly in this type of model. They're also popular right now a lot because of battery charging applications. So let's just start by running this and analyzing how the model works. One thing you might notice, if you can read the bottom of my screen, I'll zoom in once this is over. At the bottom of the screen, it's telling me what my solver was. So auto ODE 45. So that means I'm letting the tool choose for me. It's choosing ODE 45. That's a really basic solver. It's not actually a good solver to start with in this case. I've set my model up so it's telling me how long it took to run, so that was 6.4 seconds. And let's look at the results, because it is the ODE 45 is actually giving us good results for this one, so we'll stick with it. These are my outputs. So my voltage across the load and my current through the load. It's a purely resistive load, nothing special there. And then the phase angle, this is my control action. So this is my control signal. So this is particularly relevant. And then I've got some other signals that I was looking at as far as the input voltage and the current and voltage across the inductor. It is nice because if you zoom in into a couple of these, you do get to quite easily see how a DAB inductor actually works. And so you can see you essentially have control over the voltage across the inductor. And so you can apply a higher voltage and a lower voltage across it in both directions. This gives you some opportunities for partially soft switching your devices to reduce switching losses, in addition to other things like isolation. I'm not really going to get into the benefits and how a DAB works, but you can see it with this model. This is available on the file exchange. I'll link it below. But as I said, this is particularly useful for us looking at changing solver settings. So if anybody's seen my other video, they'll know that immediately we don't want to use ODE 45. ODE 45 is overly simplistic. There's a lot of Simscape electrical models it won't work for. It actually does work well for this model. I have some ideas why, but I haven't dug deep enough to guarantee that's why. So I'm going to switch to ODE 23T. Excuse me. This is, in general, the solver you should always go to first. And the simple explanation for that is that there's only certain solvers that actually work with Simscape. So I'll show you those while we're here because it's not obvious. All right. This is a good Simscape solver. This is a good Simscape solver. This is also a good Simscape solver. Just worry about these. This is the most robust, most powerful Simscape solver, so it's also going to be the slowest. This is the most generic, or most generic for a simple one. And this one is best optimized for electrical systems. Why is that? Well, all of these solvers use numerical approaches to solving their equations. They're not analytically solving everything. They're taking time steps and estimating solutions to equations. You don't need to know what's going on with that. But a trade-off is they all inject some sort of numerical error. Because of that, a lot of them, that numerical error will end up in decaying AC signals. So for an electrical simulation, we often have AC signals in them, so a lot of standard numerical techniques can actually, their error is almost amplified in electrical applications because of the degradation and oscillation. So ODE23T is particularly good at not degrading your oscillation magnitude. DAE SSD is also good at that, but it's slower. So that's why, in general, just go to ODE23T right off the bat. It's good for electrical simulations. Of the solvers that'll work, it's probably going to be the fastest for variable step. And we can run this guy. Now, ODE45 is a much simpler solver than ODE23T. But in this case, it's a little bit slower than ODE45 was, but it's not significantly slower than ODE45, because ODE45 isn't actually good with these physical networks. It shouldn't be used with these physical networks. It just happened to work. So ODE45 actually had to take a lot more steps than it normally would to solve this. And ODE23T is in general just a better simulation. You should take it as this is more accurate than ODE45 when you're doing physical models. But in general, these signals pretty much look the same, but it's a little bit slower, but it's a better model. Now, I didn't have to do anything to get this to work. If for some reason I looked at this and it wasn't converging, I'll just give you some general rules of thumb, what you can try. One thing you can do is, especially if your circuit's really fast, changing your relative tolerance, maybe make this 1e to the -4. Then you can also make your absolute tolerance match your relative tolerance. That's a rule of thumb that's going around out there. I haven't seen it make a difference, but there might be some edge cases where it does. Another issue can be is if it's if there are weird artifacts here. We're not seeing any of this case, but when you see a weird artifact, it'll be a weird artifact because we have a PID control loop. So if I saw my response going like this and it had some weird discontinuity in it, that wouldn't make sense. I was like, what is that? That doesn't make sense. How is my PI controller just injecting this? That could have something to do more with some zero crossing isn't being detected well. So you can also try switching your zero crossing algorithm to adaptive. That can sometimes help with detecting some of those. In this, it's not going to make a difference. But those are just some quick things you can try if, when you simulate with ODE23T, the model doesn't look like it's making sense. If you do those, still nothing changes, you should actually really consider, do you have a realistic model? This model here is completely based off an actual hardware design, so my parameters come off an actual hardware design. They're not arbitrary. If you put arbitrary parameters in here, there's a high likelihood your simulation is going to perform bad because you're going to have unrealistic circuits, and the time constants of them will then actually cause problems for the solver, whereas if you put in what's a good design, it will often actually simulate quite well. So those are some of the rules of thumb to use when you're approaching getting your simulation working correctly. Now, fortunately, I didn't actually have to do anything. I didn't hide anything from you. I just built this, and it worked with ODE23T right out of the bat. More and more, that's becoming the case. The MathWorks has put in a lot of effort into their solvers. They make them more robust every year, and so this actually works pretty well out of the gate. The one thing I did just to clean up the response a bit is I took this DC cap, and I went to variables, and I set it to be the same voltage as my input voltage here, just so I don't have an inrush of current and I don't have to wait for this capacitor to charge up before I turn on my control loop. So that's the only little thing I did to clean up this model as I was getting it to work. So now that we have a model that works, what can we do as far as looking at different types of simulations that are available? Well, as I mentioned, there is always DAE, this is C, so this is basically the most robust one. We'll run this, and so this is another thing to try if your ODE23T isn't working, try switching to DA-SSC and run it. And maybe you can tell just by running it that this is definitely slower. So 12 seconds. So noticeably slower than either of the two options. It's not buying us anything. We're getting the same results. And we'll actually compare the results, and I'll show you how to check your solver settings, whether you're straying. But one other thing you can do if nothing's working, I don't recommend this, but you can go to this solver configuration here. You can click Use Local Solver. Then you're going to have to pick a sample time. This is my switching frequency. So I'm doing 1 divided by my switching frequency. This gives me 1 switching period. And then this tells me how many time steps per switching period I want to simulate. For a DAB converter, this is not a high enough resolution. If this was a buck converter, if this was a motor drive, 100 would probably be more than good enough. Although I should caveat, if it's a buck converter operating under full operating range, if it's a buck converter that's limited to like 10% of its operating range, you're going to want to do 500 to 1,000 of these. But this is essentially how many steps per cycle do you need to get an accurate simulation. This backward Euler solver that is in this solver configuration block is very robust. And so it's going to be able to handle more situations than the ODE23T I was having us use, which was a global solver. I realize I haven't explained that terminology. Don't worry about it right now. Just know that this is a local solver because it's in this solver configuration block, so it only applies to the Simscape it's attached to. This is a very robust solver, but it lets you be kind of lazy with your model. So this will work better if you have unrealistic parameters and the global solver ODE23T is choking on them. This is more likely to be able to handle them, but you also have to dial the step size down really low. So I could dial this down to 1,000 steps and essentially brute force the equations. But this is going to, I'm not going to run the simulation the whole time because it's just going so slow. If you look down here, you know, it's just taking forever. Now, it will give me a pretty good idea numerically what my model is doing. So if I crank this down and get good results when everything else was getting bad results, that gives me an idea that, okay, there's something that we call, stiffness in the system. So you may have some really fast RC time constants or something like that, or you're modeling some snubbers you don't need to, just some values that are creating really high frequency content that is messing with your simulation that's not really relevant to the quality of the simulation. And so we can see this and it looks like it's doing the right thing, but it's taking forever. And we don't need to do that. But that's another thing you can do just to see where your simulation is at. If that doesn't work, like if this gives you bad results, it's, your models, the problem's probably not the solver, the problem's probably your model. Honestly, if this works and ODE23T doesn't work, the problem's probably your model and the parameters, not the solver. You want to be looking at changing model parameters. Something to think about is a lot of these components have these off-state conductances. Make sure those are all in the same range. So don't have some with like 1e to the -5 and then, come over here. Well, there it's 1e to the -9. It's not making a difference. But in general, keeping those closer to each other, keeping everything in the same order of magnitude or a couple orders of magnitude can be good. That's the sort of thing that might inject these weird high frequency time constants that you don't need that are a problem for a solver. So I mentioned you can go here, but we're going to go back to what are some of the other solver setting tricks we have available to us to try and speed things up now that this works. So what happens is, in general, I build a model and I try to get it working nice for ODE23T. And when it's working, I will actually typically go here, save it, but then I will also save it as golden reference. So this is the model where if I'm ever editing the model, this is my source of truth from a model perspective. There's still needs for validation and making sure your model's accurate, but this is my source of truth. This is my most accurate model. Now let's say I want to use this model to do a task. If I have to do 1 or 2 simulations, it's not worth the time to try and make it run faster, at least in this case. Just run it as is. But let's say you're going to do a Monte Carlo analysis, you're going to do sensitivity analysis, something where you're going to be scripting this or using another tool, and it's going to get run hundreds or thousands of times. Or even if you're just manually tuning control loops and you just want to save a couple seconds per sim, you may want to see if there's a way to speed up your model. What can you do? Well, one answer is see if you can find an average implementation of your converter, because that'll drastically speed things up. If you're using nonlinear components here, use piecewise linear components. But if you've essentially simplified the model down as much as you can get away with and you need the level of detail that's in it, now it's time to look at the solver to improve your speed. So let's look at what solvers are available. So as I mentioned already, this is general, going to be your best one. You could also use this as your source of truth, but you really don't need to. For speeding things up in a variable step, we really only have one option, which is ODEN. So ODEN is a hybrid between a fixed step and a variable step solver. You can read the help document if you want to dig in more into it, but it essentially tries to give you the best of both worlds, and it's really only applicable for applications that have PWM signals. The goal of ODEN is to essentially only trigger on these edges and not take any additional steps elsewhere. Now, you might not have to add a couple extra for it to converge, but its goal is to take as few time steps as possible and assume that your switching frequency is so high that you really only need time steps here and here, and anything else is unnecessary. Now, because we have this transformer and inductor in here with the current sloshing back and forth, that could actually be a very bad assumption for this topology. It also depends on your circuit parameters, whereas for a buck converter, taking a time step here and here, especially you might just be turning up your switching frequency to improve your THD, but you haven't necessarily changed your component sizes that much, could be way more steps than you need to get accurate transients through your inductor and capacitor. So sometimes ODEN will really speed things up, and sometimes it can actually make things worse. So we're going to investigate how do you go about trying to use ODEN. So first you'll see it gives you, the first thing you need to think about is the integration method. And this is also not clear, but only 2 of these integration methods will be useful for Simscape, ODE14X and ODE1BE. The rest of these are not effective for use in Simscape. Now again, ODE45 was working on this model, so I can probably get away with something like ODE3 and ODE4. But in general, when you're using Simscape, you should use ODE14X or ODE1BE. Backward Euler is the faster one. And so we would start with that. Well, we want the fastest possible. We'll just run it. Just try and run it and see what happens. If you have a long simulation, go here, turn your sim time down. You're just trying to get a feel for what your simulation speed is on these. So if I use this as is, 0.2 seconds. So that's super fast. Oh, well, it also gave me garbage as my output. So that's not very promising. So it requires a little tweaking to get realistic models. So the first thing that you really want to look at with ODEN is this max step size. So the max step size sort of forces it to take additional steps into just those transitions of the PWM signals. So if I want to do that, I'm going to go in here and actually pull out my switching frequency. I really should have hard-coded this, or not hard-coded this. I really shouldn't have hard-coded this. I should have made it a variable that I could reference. But I can start by saying, well, I'm just going to make sure it's taking at least one sample per cycle. This is kind of unnecessary because it should be doing that already. We're going to start with that and then slowly decrease the time step until we start getting something that resembles reality. Well, this is more realistic, but it's still garbage. So let's make it take 2 samples per cycle. It's getting slower. The results are getting a little bit better, but not much. What if I make it take 4 samples per cycle? So now it's gotten a lot slower. We're at 5 seconds, so we're barely saving any time at this point. And it looks like I'm mostly getting good results. Now I've been staring at this enough where I know that this overshoot is actually noticeably higher than the other approach. So there's still a decent amount of error in the system, but it's at least converging to something moderately realistic. And it's bought me maybe 10-15% in speed. But there's a decent amount of inaccuracy. One other thing you sometimes need to think about is the number of Newton iterations. Now, I can tell you since my model is accurate with ODE 45, I probably don't need many more Newton iterations. This becomes more relevant basically the more you're actually using the Simscape solver, its capabilities. But 3 to 5 is, for complex systems, a more likely place. So sometimes you turn up the Newton iterations and that will improve your accuracy without changing your time step. But it's also going to slow things down. So I've turned it up to 5 Newton iterations now, and it was taking 5 seconds. Now it's taking 8.8 seconds. So now it's slower than 23T, I think. And the bump's still there. It hasn't really changed anything. So, and this isn't actually surprising. Rule of thumb, OD1BE, very simple. Don't always need that many iterations. It's most likely to work for something like a motor drive. It plays nice with these 3-phase systems where everything's balanced. Doesn't work as well for DC to DC converters. OD14X typically works better. So we can go back to 1 if we want. This will by default be at 4. You probably want to drop it to 1 if possible because it'll be faster. It's how many times it does a calculation per time step. We'll run this. So this is 6.2 seconds, so not a lot of speed up. And this is also inaccurate. Now this is much more accurate than backward Euler was at this point, but that's still not good enough. So we have to go back and change this to 2. And one thing I should mention is you sort of need to compare your times of your models at the same time, because you will get different speeds here depending on what else your computer is doing. So everything was running a second faster when I was doing this stuff earlier this morning. I don't know what's changed, but so don't compare times over the course of drastically different situations for what your desktop is doing behind the scenes. So this is 7.7 seconds. This is the bump is lower, so this is closer to reality. So it's okay. But let's check again what happens when we're ODE23T. Variable step ODE23T. ODE23T doesn't need a max step size, so we're just going to let it do its thing. It was doing just fine without that. So I think it's going to be slower. Yeah, 9.4 seconds. So we found a way where, okay, we can actually save a couple seconds per simulation time. It's looking promising. but we did it very roughly. Just looking here. What do I actually need to do to verify that it's good enough? If I was being honest and doing this legit, I'd take these signals, go to Simulation tab and click Log Signals. Now I'm going to run this. So this is 23T, this is my golden reference. I just realized it's running slower because I'm recording this. And let's get rid of all of these. Then I'm going to rename this as my golden reference, OD23T. And I've got my current here, my phase here. I could put my voltage here if I wanted. And those are useful. Now I'm going to go back to my other settings I just had that looked promising. And I'm going to go ODN, paste this back in, so I need to do 1 divided. It gives me per cycle. And then I needed 2 per cycle for 14x. Hit apply, hit OK, and hit run again. And so now that I've found something that looks promising, I'm paying a little bit more attention to what the response is and comparing it. So I go back to simulation. I've got new data. So the first time it will have archived my old run and put up the new data here. So I actually need to go back here, turn on iLoad, and immediately say, oh, I mean, that's not that different, but that is different. Phase. Oh, that's actually very different. And vload. It's going to have the same difference as the current. So this brings up a very good point in that do not just look at your closed loop response, because your closed loop controller is probably going to make it look better than reality. Whereas if you look at your control response, these are obviously different. So this error is not actually looking acceptable. I have 2 very different steady state operating points, whether I'm using ODN or whether I'm using OD23T. Now, again, I am demonstrating this on probably one of the worst topologies to actually use tricks to speed things up. The tricks I'm showing you where you try to go to fixed step or you try to go ODN work a lot better for stuff like buck converters, standard inverters, and drives. So they can be very useful, but this is what you need to do. You need to start with a golden reference in 23T and compare your results. And if they look good, then take the speed savings. But if they don't, you might actually just be better with OD23T. Now, one final thing that you might do to speed things up is to just go fixed time step. If you ever run your model in a variable time step and it is just taking forever, and we're talking it's taking forever per cycle. It's not that, oh, you tried to simulate, you know, 1 million switching cycles and it's taking a long time. It's like, no, you're trying to simulate 10 to 100 switching cycles and it's taking forever. If that's the case, you have something what we would call stiffness in the system. That stiffness might be something that you can get rid of by changing parameters, or you might be lucky and you might be able to just say, let's use a fixed step solver and step over it. Now, in the case of this topology, 100 steps per cycle isn't actually going to bias anything. It's going to make the solution much slower and be less accurate. But again, this is the worst topology for that to work. A place where that's much more likely to improve your accuracy would be MMC. So in MMC, you could have hundreds of PWM signals all triggering different zero crossings. And fixed step solver doesn't care how many zero crossings there were. It's taking the same amount of steps no matter what. So the fewer transistors you have, the less likely a fixed step solver will help you. The more transistors you have, the more likely a fixed step solver will help you. The other reason this doesn't do well with a fixed step solver is because so many of these PWM signals are synchronized. So I don't actually have that many I have fewer zero crossings than I have transistors, especially because I'm not simulating dead time right now. If I simulated dead time, I think I would double the number of zero crossings. So I would probably double my simulation time just to add dead time to this, which is something you want to take into account. What you're looking at, is dead time going to affect the analysis, or is dead time not that important? So this is taking much longer. And you can see you've got these weird artifacts. So these are those weird artifacts that if you see these weird artifacts with a variable step solver, that's when I was talking about, go try turn on adaptive zero crossing. Because you really shouldn't see something like this. Because the systems should respond in a more continuous, periodic manner. Because that's the way they're designed. But this just isn't even useful in this case, so we don't want to use this local solver. At least with that, we'd have to increase the number of steps even more, so it would be even slower. So for this topology, we're actually in general just best using ODE23T. And this is honestly, this is what I typically do. I typically am just leaving my models in ODE23T unless I need to do something like take them to real time, in which case you need to find a fixed point for them. But ODE23T works quite nice, and you're good to go with it. So I will do some follow-up videos where we actually get into what is going on, why are there solvers that work with Simscape, and why are there solvers that don't work. The clue is it's called a DAE. What are some of the details of what do variable step solvers do behind the scenes? Like a difference between ODE23T and ODN is ODE23T is tracking its maximum potential numerical error, and ODN isn't. What does that even mean? I didn't explain enough. Some of you might know what that means, but some of you might just be like, what in the world are you talking about? I can get into concepts like that in a separate video, but this video is much more just how can you go about this? What can you do? Another thing that will be useful to go over that deserves its own video, but at least make it aware of. When you have a model like this, you can do a solver profiler. And you can go to performance, well, let's say performance advisor, but you want to go to solver profiler. This will run your model and track a lot of extra information. And so if you've got Simscape in it, you probably want to click model Jacobian, model Simscape, Simscape Stiffness. You can specify what points you want to model that at. So I'm going to just put it basically a third into a switching cycle. And I don't need to simulate this for its whole time. So like 100 switching cycles, and click run. And this will give you a lot of insight to what this is particularly relevant when you have a variable step solver. This will give you a lot of insight into what is going on with your model. When are these things I call zero crossings happening? What's going on? And what you can see, just at a quick look, is you're essentially getting periodic zero crossings because of how the PWM signals are lining up. And so you have that zero crossing, you take a really small step, and then you jump back up to a higher step size. So right here, our step size is super small, but then it immediately jumps back up to a larger step size. And that has a lot to, your average step size has a lot to do with your simulation speed. There's nothing you can do to get away from the fact that you need to stop every time there's a PWM signal. So sometimes this doesn't really tell you much, because like you have to do this based on when the PWM signals are triggering. But if for some reason, if it goes down and it stays down here, and it's taking like 100 steps down here before it pops up again, that tells you there's something in your circuit that's really high frequency content besides the switch just turning on that's keeping it stuck at a low time step. And so that's where it's like, okay, am I modeling some snubbers I don't need to model, or some parasitics I don't need to model, or maybe I need to add more parasitics, maybe start adding additional parasitics to sort of damp out that behavior. Those are things we can dig more into later. I just wanted to say this is out there, so use it. I will be releasing more videos I haven't ever intended to release the one video. It was just to help out a professor who was teaching a course, literally needed a crash course for their students to get them ready for the course they're going to take. So I just sort of released it to help them out. But then there was a lot of positive feedback. And I don't think there's a ton of topics I can go over that justify these types of videos for a long period of time, because there's only so much the average user needs to know about Simscape Electrical before it's not worth to specialize anymore. But I can certainly go over a lot of the fundamental concepts of solvers and different approaches to modeling circuits. And then, maybe if there's demand, we can switch over to LT Spice, or actually talk about, actually start digging into specific topologies and other things like that. We'll see where it goes, but I will at least release some more videos talking about what's going on behind the scenes with solvers, how to use these diagnostics tools. Another good idea that a lot of people are interested in is taking advantage of different level fidelity blocks that are available. So these are all things that the solver stuff's pretty generic. I'll teach it relevant to how MathWorks happens to implement it, but it's good generic information in general, because any other simulation tool needs to take advantage of solver realities as well. And the fidelity discussion, again, it will be specific to the MathWorks tools, but it's applicable to other tools that offer you varying levels of fidelity as well. So if you like this kind of stuff and have ideas for what would be helpful for you to see, please leave it in the comments, because I will be more intentional about creating some more content, at least short term, to get some of the basics out there. You do not need to like or subscribe, but please leave comments with questions you have. Thank you for your time.